Hello and welcome to today's webinar. I'm Anita Ramanan. I'm a quantum software engineer working in Microsoft's quantum computing group. And I'm here today to talk to you about harnessing the problem-solving power of quantum computing. Now, my background is I studied a master's in atomic and particle physics and physical chemistry back at UCL. And after that, I immediately joined Microsoft as a graduate and have been focusing more on software engineering ever since. In the last kind of year and a half or so, I've been working quite closely with the quantum team. And in October last year, I officially joined as a quantum software engineer and have been working on something called quantum-inspired optimization methods ever since. Today, I'd like to talk to you about what Microsoft is doing in the quantum computing space. Why would we care? What can we use a quantum computer to solve? I'd also like to quickly look through how you build a quantum computer, what we're doing in that space, as well as introducing Azure Quantum and our quantum development kit. I'll then spend the second half of the talk introducing how you would go about coding up a quantum algorithm called Grover's search algorithm using Q# in our quantum development kit. But first things first, we need a reason to do all of this. Why would you want to build a quantum computer? Now, the answer to that question is much more varied than what we see on the screen right now, but these are the kind of four areas that we at Microsoft are really focused on solving with a quantum computer. So let's start with simulation. This involves taking problems that are too complex for us to solve analytically using a classical machine and using a quantum computer to solve them instead. For example, simulations that involve elements that sit in the transition metals or the lantanides and actinides. These involve the electrons in these elements exist in orbitals that are very, very closely packed relative to some of the kind of simpler metals, for example. And therefore, we need to be able to take into account the Coulombic interactions between these electrons in order to sufficiently simulate these things. We can't use approximations such as density functional theorem. Now, to simulate these Coulombic forces, it requires a quantum simulation, and this is beyond our ability to accurately do on a classical machine. We need something like a quantum computer to be able to attack these problems, we think. This can be the results of this can be wide-ranging, everything from designing, say, better catalysts to tackling world hunger or climate change by designing fertilizers that work or that we can produce more efficiently. Or sorry, designing ways in which we can produce fertilizers more efficiently. Cybersecurity is a second focus for us. You may have heard of this, this kind of upcoming apocalypse where RSA encryption is going to be broken by quantum computers, but it's not quite as dire as it sounds. Yes, quantum computers will be able to exponentially, more efficiently factorize large numbers down into their prime factors, which is the core of what an RSA encryption algorithm uses to secure our data. Now, whilst a classical machine would take something like 1 billion years to actually brute force an RSA 2048 key, a quantum computer could do this in about 100 seconds in theory, which is a problem for you if your secrets are important for more than 100 seconds at a time. Fortunately for us, there are ways of both encrypting information using quantum computers. So, for example, quantum key distribution can be used to exchange cryptographic keys. Or we can actually just encrypt our information classically, but in a way that doesn't rely on this fact that factorizing large numbers is very difficult for a classical machine. We use ways that are resilient to quantum attack in the future, but that we can do classically. This is called post-quantum cryptography. And if you're curious about it, we have a whole research team who is very focused on developing new methods to do this. And if you just search Microsoft post-quantum cryptography, you'll be able to find the site and all the relevant literature. Optimization is another area that we're looking at right now. Now, I mentioned briefly that this is what I'm focused on. So this is a kind of area where we take a quantum algorithm that's designed for optimization. usually at the core of which lies a quantum random walk. And what we do is we dequantize it. We take out that quantum random walk and replace it with a classical random walk. Now we can implement this on a classical machine using classical coding languages like C or C++ or Python. And we're actually seeing speed up over some of the best-in-class traditional methods, the classical methods today. For example, we're working with Case Western Reserve University to optimize the way that they generate pulse sequences for MRI scans. Now, working with them, we've actually been able to reduce by 2/3 the amount of time that it takes to do an MRI scan. We're also working on traffic congestion problems, for example, taking large number of cars traveling at rush hour, giving them a number of different options for the routes that they could take, and then optimizing to minimize either the global congestion across this system or the amount of time that they take to get to the destination, or a number of other factors that we can bring into this problem. So these are results that we can see now, today, and then accelerate further when a real kind of at-scale quantum computer is available, when we can unsubstitute that quantum random walk, so we can get another speed up there. The last example up on the board is machine learning. Now, this is a very new field of research. Quantum machine learning is, as you might guess, a quite exciting field of study. The problem is that it's very costly to transform classical information into a format that the quantum computer is able to deal with. So instead of taking, kind of a big data problem and then doing these kind of machine learning algorithms wholesale on them in a quantum computer, potentially we can be looking at problems where there's a small input, a small output, and large compute in the middle. So we can apply quantum computing for specific parts of a machine learning problem. This, as I say, is obviously a fairly new area of research, so it's one to keep an eye out on. What makes quantum computers any different to a classical machine? I'm talking about these things that we're not physically able to do in a classical machine, and probably will never be able to do. But why would a quantum computer be any better at it? Fundamentally comes down to a few kind of quantum phenomena. The first one of which is superposition. And this is the one we'll be focusing on today. Now, on the left-hand side of the screen, you'll see a representation of the classical bit, the binary digit, the fundamental unit of digital information. A bit can be either 0, off, or 1, on, like the light bulbs and the two left-hand side light bulbs. It can't be anything else. A quantum bit, or qubit, on the other hand, can be both 0 and 1 at the same time, as the kind of colloquialism goes. You can kind of think of it more like this dimmer switch. It can be in a probabilistic superposition of both 0 and 1. Most importantly, we can use this qubit in superposition in combination with a bunch of other qubits and manipulate the probability that when we take a measurement to collapse the superposition and give us either a 0 or a 1 out at the other end, we can manipulate the probabilities that we actually see either of those results. And that's one of the key differences, something that we can't do on a classical machine. We do tend to use this kind of maze analogy to kind of help us understand a bit more about how we can leverage this superposition. This is actually an analogy for the Grover search algorithm, which is what I'll be talking about in the second half of this presentation. But effectively what we have here is we have, say, a database of all of the different ways in which we could travel this maze. And classically, it's unsorted, we have no idea where to start. We're limited to just trying different options, one at a time, until we arrive at the correct solution, the right way through the maze. As you might imagine, that's not particularly efficient. We could get really lucky. We could, find it on our very first go, but we could get really unlucky and find it on our very last. Either way, it scales with the size of the problem of the order of n being the size of the problem. What happens if we do this on a quantum computer? In this instance, what we do is we take all of the possible routes that we could take, these kind of items in our database, each one representing a solution, and we put them into a superposition altogether. We can then manipulate, whilst in the superposition, the probability amplitudes of each of these different paths. So we manipulate them, we make it more likely that when we measure, we'll see the correct one. And again, we boost that probability amplitude until finally we take a measurement and collapse that superposition down. And at this point, if the probability amplitudes are represented by the thickness of these lines, because the answer that we're searching for is so much thicker than the other lines, higher probability amplitude, we're much more likely to see the answer come out when we take that measurement. Now, this is still probabilistic. You would still have to repeat this a number of times in order to be sure that this is the answer that you were looking to find. But we find that this is actually of order of root n. So it's a quadratic speedup over the best case classical. How do we represent information like this? With a classical bit, it's fairly straightforward. It's either a 0 or it's a 1 at any one time. Fairly simple kind of notation. To represent this notion of superposition, we need a new way of describing these states. And this is where this notation comes in. This is known as Braket notation, invented by Paul Dirac. On the left-hand side, we have psi. Psi is in this kind of weird pointy bracket. That's just called a ket. It just represents a column vector. If that arrow was on the other side and the psi was in the middle here, it would be called a bra, and it would represent a row vector. So they're just vectors. So we have our two basis vectors, 0 and 1, exactly the same as we have classically. And each of them is assigned something called a probability amplitude, alpha and beta. Now, these are a measure of the oneness or the zeroness of the state. The really important thing to know about a probability amplitude is that unlike a classical probability, which must be a positive number, a probability amplitude can be negative, it can be complex, it can, of course, also be a positive number. But because of this nuance, the fact that we can have negative probability amplitudes and complex ones, we're able to use them to interfere. Just like waves, we can constructively and destructively interfere with these probability amplitudes whilst in superposition. And that's how we amplify that possibility of seeing the answer we're looking for. So we get the actual probability of seeing a 0, for example, when we measure by taking the modulus of the probability amplitude alpha and squaring it. Likewise, for the 1 state, we do the same to beta. As with any other probability, the total probability of seeing either the 0 or the 1 when we actually do that measurement has to add up to 1. Otherwise, you've got some third state which it's not possible to get out of that superposition, and you've broken physics. So let's look at this in action. So this is a quantum gate. It's called the Hadamard gate. It does an operation on a qubit, on a single qubit. In this case, we're going to feed it the pure state psi equals 0. There's no superposition here. It's just in its 0 state. And what we get out is a superposition state. The Hadamard gate is used to introduce superposition into our quantum system. This is an equal superposition. Both of those probability amplitudes are the same, and if you take the modulus and square them, you get a half for each different 0, for either 0 or 1. So it's 50-50. What happens if we put 1 through the same Hadamard gate? This time we get a very similar one, but you'll notice that there's a minus sign there in front of the 1 part of this equation. Now, experimentally, this makes no difference to us. If I took a measurement of the first state or the second state there, I would see, I would not be able to tell that one had a negative probability amplitude. The reason being that when you take the modulus and square it, both of them still give a half. So they're indistinguishable to me by measurement. But we can use that minus sign to do this interference, which we were talking about. Now, just as a heads up for later, that top state, the 1 over root 2 0 plus 1 over root 2 1, is known as the plus state in shorthand, and the lower one is known as the minus state, just to represent the change in sign there. We'll be using that later. So what happens if I take 2 of these Hadamard gates and jam them one after the other, and then apply them to my 0 state? You might think that maybe we'll get something kind of complicated out, or we'll get some still combination of 0 and 1. But in fact, what we see is that we get out exactly what we put in, as long as we don't measure in the middle. How does that work? So let's say we start in the 0 state, just for the sake of argument. Let's describe this like a probability tree. So at each level of this probability tree, we have equal probability of measuring any of the states listed. We apply the first Hadamard gate, and we get 0 plus 1, with 50-50 likelihood of measuring either of those. We then apply the second Hadamard gate. Again, on the 0 side of things, we get a 0 plus 1. But when we put a 1 into the Hadamard gate, if we remember from before, we get a 0 minus 1. Obviously, we're ignoring the 1 over root 2's here, just for simplicity's sake. Now, from here, it's fairly straightforward to see that the plus 1 and the minus 1 are going to cancel out. That is an example of destructive interference. And the two zeros will constructively interfere, which is why we end up with just 0. If you're curious about what this looks like mathematically, this is it. Now, after the first Hadamard, we get this plus state superposition, like we expect. And then if you expand out the brackets on the final state, you find that we get a half 1 minus a half 1 gives us just the 0 state. And that is how we use interference. Okay, so I've spoken a little bit about what makes a quantum computer special. How do we actually go about building one of these machines? There are a number of different ways in which to approach this problem. The first one, the kind of most common way, is to find some sort of quantum system, one that can have a two-state system. So, for example, if you take an electron can either be spin up or spin down. We've got a two-state system. Great, we can use that for computation. We can represent, say, 1 as upstate and 0 as downstate. Fairly straightforward. We also need to be able to manipulate that, to use, say, laser pulses, for example, to excite these electrons or whatever other quantum system we're using, and to put them into superpositions and to perform computation. Now, this is, you'll hear things about ion trap qubits or superconducting qubits or other kind of various different types using these kind of the kind of local properties of these quantum particles. And these are known as noisy intermediate scale quantum devices, NISQ devices. The reason for the word noisy there is that these particles are incredibly susceptible to noise from the environment. That could be anything from the environment heating up a little bit. You can never cool anything down to absolute 0, so there will always be temperature or some heat in the environment. It could be something like a cosmic ray that you're just not able to shield your experiment from. It doesn't matter what the source of the noise is. The problem is that any interaction with that particle counts as a measurement on that particle. And it will ruin any nice kind of quantum state that you've set up. This is known as decoherence, i.e., the loss of this nice coherent quantum state that we want to use for compute. So how do we protect from this? There's a lot of research being done into this, as you might imagine. One way to do it is to invent a better qubit, a qubit that is more stable by default. The other way is to apply something called quantum error correction, which means that we just have a bunch of spare qubits, effectively, which are there to detect and fix errors when they're detected in a single qubit. And this combination of error-correcting qubits and the actual qubit you're trying to correct is called a logical qubit. So at the minute, we need something of the order of 1,000 error correction qubits to make up a single logical qubit. The problem here being that as you add more logical qubits, obviously the amount of error correction qubits and everything kind of scales out quite rapidly, and that introduces more noise, which introduces more error, which is a bit of a problem. So at Microsoft, we decided, okay, cool, so error correction is clearly a useful thing to pursue. But instead of building ion traps or superconducting qubits, let's see if we can focus on something that should be inherently more stable. So we started looking at this thing called a Majorana Fermion. Now, this was proposed by Michael Friedman, who's a Fields Medal-winning mathematician, about 20 years ago. He said, well, instead of using the local properties of these quantum particles, why don't we use the topological properties of a group of particles instead? So we kind of, did some research. We've chosen the Majorana Fermion. And this is what we're trying to use for computation to represent our qubits. How does that work? So what we do is we take a nanowire and we put it in something called a dilution refrigerator. You might have seen these kind of big, giant, golden chandelier-y looking things. And what this does is it takes materials from kind of room temperature at the top through liquid nitrogen temperature at 77 Kelvin, liquid helium at 4, and then it cycles 2 phases of liquid helium to get us all the way down to 15 millikelvin. Now, this is pretty much the coldest place in the universe. It's colder than deep space. It is, to put it into perspective, at somewhere very close to minus 273 degrees Celsius. Pretty cold. Now, when you put these wires at this temperature, the electrons in the material start behaving weirdly. You start forming these kind of chains of electrons with a half electron, kind of imaginary, half an electron cap on each end. And we can manipulate these strings. We can braid them together. And this braiding is how we represent our quantum operations. Now we can bring the ends of this together, and the 2 electron halves will either annihilate to produce no electron, or combine to produce an electron, and that is our 0 and our 1. So that's how we do measurement. But because they're physically separated, because we're using this topological property, these braids, like you can see here, we're much more resistant to noise. So if you can kind of imagine like time being along the vertical axis there, and these being our fermions, we're doing a whole sequence of operations by braiding. Now, on the right-hand side, you see a situation where we've had some noise enter the system. The braids, they're wiggly. They're not these kind of nice, pretty states anymore. But just like if, I got a bunch of strings and tied them together and then shook the knot around, the information encoded in that knot would still remain there. This is a similar idea here. The information encoded in this braid pattern remains the same. We don't lose it if there is perturbance, to a point, of course. The other thing that we're focused on at Microsoft is Cryo Control. So not only do we need to build these kind of stable qubits, these topological qubits, but we also need to define or design control hardware that's capable of actually working at cryogenic temperatures and controlling, sending information and control to these quantum particles. So our Sydney team recently had a breakthrough around this. They have invented a new way to control these qubits using up to 50,000 qubits, using only 3 control wires, which are the kind of blue wires that you can see exiting at the bottom right there. Now, on the far right there, you can see the actual Cryo Control chip. It's the kind of top part of that chip. And then in the kind of middle section, that navy part, you can see 6 qubits embedded. And we can control, theoretically, up to 50,000 using just these 3 wires. Now, this is important for 2 reasons. One, the more wires you have, the more noise you're going to introduce to your system. And 2, there's only physically so much space you can actually attach wires to your chip, right? Like if you need 10 wires per qubit to control the qubit, you're going to run out of space very quickly, just physically. So it kind of limits your scale. So this should enable us to scale much more effectively in the future. This brings us on to Azure Quantum. So this brings all of our quantum efforts into a single place. It brings our quantum solutions that we're developing and deploying today with customers, those quantum-inspired optimization solutions, plus some quantum-inspired kind of more generic solvers. These are in private preview right now, but there'll be a link later on in the slides so that you can sign up for private preview when it's available, to Azure Quantum in general, I might add. It also brings our quantum software efforts into one place. So this is our quantum development kit, all of the simulators, all of the resource estimation tools that we've made available. All of that's available through Azure Quantum. Also, it's all open sourced on GitHub if you are curious. This also brings our quantum hardware efforts into one place. Our work on Cryo Control, our work on the topological qubit, And not just our qubits. We're actually partnering with a number of different hardware partners, such as Honeywell and IonQ, who are manufacturing ion trap quantum computers, and QCI, who are manufacturing superconducting qubits. So you'll be able to, with a single line of code change, actually run Q#, our quantum language, algorithms on real hardware of various different types. So I've mentioned the Quantum Development Kit a couple times. What do I actually mean by that? It's comprised of a few different parts. The first part is the code. So much like with a machine learning algorithm where you have a kind of a core piece that's the CPU, runs on CPU, so the kind of basic I/O and all of the kind of data prep and things like that. And then you call out to a GPU to accelerate where it'll actually provide a speedup. Whilst theoretically you could run everything on the GPU, it would be expensive and a pain to code. And I mean, CPUs are pretty good at a lot of things. We spent a great many years optimizing them. You can think of quantum programs in the same way. We have Q# code, which runs on the actual quantum hardware. But we have also driver code, which is written in a classical language, such as C# or Python. You can run it in a Jupyter notebook. And that does the kind of data prep and the I/O and the visualization, etc. And then again calls the Q# on that quantum hardware when you'll actually get speed up from it. The Quantum Development Kit also contains a large number of kind of useful functions that are contained in libraries. We have things like there's a numerics library, a chemistry library, which is quite handy, as well as lots of useful functions. So, for example, instead of having to implement the quantum Fourier transform every time you need it, which is quite frequently, you can just call the QFT operator from the QDK libraries. It's very handy. We then have, obviously, unfortunately, there's no real quantum hardware available at scale yet. So instead, we need to run things on classical simulators. This is where the classical runtime comes in. So you can use the full state simulator, which basically mathematically simulates the state of all of the qubits in your system. Unfortunately, this is kind of RAM bound, memory bound. On a laptop with about 16 gigs of RAM, you can run up to 30 qubits, depending on what else you've got running. If, to run every time you add another qubit, you double the amount of RAM that you need to store all the information. So once you get to, 40 qubits, you start needing 16 terabytes of RAM. 50 needs something like 16 petabytes, at which point you're kind of reaching the limit of the biggest supercomputers that we have built to date. So possibly not going to get much further than 50. We also have, to get around this problem, a couple of other different simulators that can simulate larger number of qubits by kind of cheating effectively. The trace simulator, for example, instead of simulating that, all of the different quantum states that could exist in superposition, relies on you to provide it with measurement probabilities, which means that it doesn't need to deal with that kind of level of simulation, but does allow you to simulate many, many more qubits in order to kind of benchmark and test your algorithms. The TOEFL simulator limits you to a specific subset of gates. Similarly, allows you to kind of debug programs and optimize them. The resource estimator is actually in use by our teams right now. This is allowing us to understand how our quantum algorithms scale with the problem size and optimize them so that we'll be able to run them on the smallest possible hardware set that is available at the whenever it comes into kind of commercial use. Then, of course, when a real quantum computer is available, we want to easily be able to switch between the simulator code and the code that runs in a real quantum machine. That's very straightforward with Q#. All you do is you change the target. It's a single line of code. You say instead of, I'm targeting online simulator, you'll target IonQ. And that's all you need to do. All that needs to be done on the kind of back-end side is a compiler needs to be written for that particular hardware. But your Q# can stay the same. Now, I mentioned that this is all open source earlier, but it's also available for Mac, Linux, PC, Windows even, for free. You can download the simulators, you can download QDK, and go and have an explore. I'll have some links at the end of the deck as well. So before we get started with the Grover search algorithm walkthrough, we're going to need 4 quantum operators, 4 gates. The first one should hopefully be kind of familiar if you've ever done any kind of classical computer science. This is the NOT gate, the X gate. All it does is it takes a qubit that is in the state 0 and it flips it to 1, takes a qubit that's in state 1 and flips it to 0. It just flips the state of the qubit. It's super straightforward. The Z gate is a little more quantum. The Z gate does nothing to a 0, or a state that you put in when it's at 0, but it applies a -1 phase when you pass it in a 1 state. That'll be important for a few operations in a minute. The Hadamard gate, we've already seen this one, takes the 0 state to the plus state, and likewise, or alternatively, takes the 1 state to the what we call the minus state, as we can see the kind of expanded version on the slide. And the last one is measurement. So it's not strictly a quantum kind of operator in the same way as the other ones are, but effectively this is, what we do when we take this measurement, and what we get out is a classical bit per qubit that we measured. So we'll either get a 0 or a 1 result out. So let's get to using these. Firstly, let's introduce Grover search. Kind of spoke a bit about this earlier. The problem setup is we have a database, we have n elements in that database. We know that we want to find one of those. We know what that one is, but it's unordered. So, we have no kind of efficient classical way of doing that other than this kind of force method. What we do is we need little n qubits. So to represent, say, 8 bits of information, we need 3 qubits, because 2 to the power of 3 is 8, and we can hold 2 to the power of 3 pieces of information with 3 qubits, or bits of information, sorry. So in this instance, we're going to have small n being 3, because just for simplicity's sake, for the demonstration. But obviously, this could scale up to a much bigger problem size. And what we're going to do is we'll start with all of our qubits in this nice 0 state. Everything is 0, so that we know kind of it's a good known starting state, so we can start our computation. So the very first thing we're going to do is we will prepare our states for search. Now this is just using the Hadamard gate, which we've seen a couple times already. So we apply the Hadamard gate to the 0 state that we start with to get the plus state. This gives us 1 over root 2, 0 plus 1, as we saw previously. What happens if we apply that to a larger system? Fairly kind of logically, we get, if you apply the Hadamard n times to n qubits, you get n pluses. And then you can see the expansion there on the right-hand side. In our case, we're just limiting this to 3, so it simplifies down a bit. So we get plus, 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 and then if you expand that out, you wind up with this equation. So 1 over root 8. I'm not going to read all of those out, but you get the idea. We have 8 different states that this could possibly exist in. Sometimes you might see these states represented as, instead of in their kind of binary format, as this decimal representation where you have 0, 1, 2. It's the same thing, it's just written differently because we're lazy. So I'm going to be using this kind of graph to represent what the probability amplitudes of the states that we're looking at look like throughout these manipulations. So initially we start with this nice uniform superposition, which is what we've just done with the Hadamard gate. If I took a measurement at this point, I would be equally likely to see any of the states, any of these 8 states. That's not hugely useful. What does that look like in code? So this is what an operation looks like in Q#. We define an operation using the operation keyword here. This is the input. So this is going to take something that we're going to call database register, which is a qubit array. If we wanted this to just take in a single qubit rather than an array, all we'd need to do is get rid of those square brackets. But in this case, we have a register with multiple qubits, hence the square brackets. This here, after the colon, is this unit is the return type. Unit in Q#, you can kind of think of like void. It doesn't return anything. It just does stuff to the qubits. Then this highlighted part is ADJ and CTL. This is an important one. This flags to the compiler that this operation is adjointable and controllable. What do we mean by those? Basically means that so the adjoint of an operation you can kind of think of as it's kind of reverse, right? So Hadamard happens to be self-adjoint. That means that it is its own adjoint. So you do Hadamard twice, and as we saw earlier, if you put 0 in and you do 2 Hadamards, you get 0 out. But that's not necessarily the case for other operators. So if you define your own custom operation here, you can do a bunch of different things within it, and that might not be self-adjoint. If you just use these flags here and don't specify an adjoint in the actual body of this operation, the compiler will actually figure it out for you. It will automatically create an adjoint version, and if you call that later on in the code using this functor here, it will just use that particular auto-generated version. If you happen to have a more efficient version of this yourself, or a particular preferred way of doing it, you're absolutely free to implement your own. You would just add, there would just be more in the operation body down here, where you specify the adjoint. Now the controlled version, a controlled gate, like a controlled NOT gate, for example, will only apply the operation that is being controlled if the control qubits are all in the one state. So say, for example, we had our 3 qubits, and they're in state 0, 0, 0, and these are our control qubits. Nothing will happen if we wanted to do control on this qubit, using these two as the control. So this is the target. This, on the other hand, both of our control qubits are in one state, and therefore we will have an effect on the target qubit. Let's say we're to control X, we could do this, for example. It would now go to 1, 1, 1. Fairly straightforward. And we do that by applying the controlled functor. So here are the control qubits. That has to be a qubit array. If you just have a single qubit, you can just stick square brackets on the outside of it, and that turns it into an array. And this is our target qubits. The actual part where we're applying the Hadamard to each of our qubits, we have this convenient apply to each method from Q#. Now, normally we would need to say Hadamard qubit 1, qubit 2, etc. This allows us to just specify an operation to apply and the selection of qubits to apply to in an array, and just it does it for us automatically without having to write loads of for loops, which is quite convenient. So this is the state that we find ourselves in, this nice uniform superposition. The next thing we want to do is selectively apply a phase shift to the element that we want to find. This is our marked element. In this case, we've just arbitrarily chosen it to be 0, 1, 0, our 2 state. Now, it's important to note that even in this configuration, if I took a measurement, I'm still equally likely to see any of these states, because as we saw before, the probability amplitude being negative, I can't measure that. I have no way of telling. It's the magnitude of that amplitude, or of that probability amplitude, that is the important part for the measurement. So I still not really achieved anything much here. But how do we do it? It's a kind of first important step. So what we want to do is we want to be able to reflect about the 0, 1, 0 state in order to produce that minus sign in the phase. How do we do that? Well, hopefully me mentioning the minus sign should remind you of that Z operator we introduced. If you recall, Z applied to 0 gives us 0, doesn't do anything. But Z applied to the 1 state gives us minus 1. It has this minus phase. Whoops. And that's exactly what we're looking to do here. So how do we apply this to multiple qubits? Using that controlled functor that we found out about just a little bit earlier. So in this case, we're going to do controlled Z on, so as we discussed, we've got 3 qubits control will only activate if the first two qubits are in the state 1. There's only two configurations where that happens. We've got 1, 1, 0 and 1, 1, 1. So in this case, these are our control, and this is our target qubit. So in the first instance, control activates because these two are in state 1, but because we're applying the Z operation, nothing happens because Z applied to 0 gives us 0. So we end up with 1, 1, 0, just like we started. In the second case, however, our control again activates because of the first two being in 1, but this time we're applying the Z gate to a 1 state, which gives us that -1 phase. We end up with -1, 1, 1. This is the phase shift we're looking for. Great. So all we need to do to apply a phase shift selectively is to find a way to manipulate our current phase, to change our current state, to change the basis into 1, 1, 1, apply the control Z, and then undo that operation to give us back our original state. So if you recall, our marked state, the one we're looking for, is 0, 1, 0. So the first thing we want to do is turn it into 1, 1, 1, so we can do that control Z operation. This is where the X operator comes in. So if you remember, X applied to 0 just flips. Gives us 1. And X applied to 1 gives us 0. So we're going to use this on the first and the last qubit in our register. So I'm just going to call this reg as shorthand. So in C#, or Q#, sorry, what this looks like is X applied to reg 0, 0 being the index of the first element of the register. And then we're going to do X applied to reg 2, which is the third. And this brings us to 1, 1, 1. Now, the important thing to note is that this only brings us to the 1, 1, 1 state if our current state, the one that we're looking at, is 0, 1, 0. In all other cases, it gives us some other combination of zeros and ones, but not the all ones state. The next thing we do is, of course, apply our controlled Z. How do we do that in C# or Q#? We use the controlled functor. We just specify the gate, so controlled Z. We now need to specify our control qubits. So those are the first two qubits in the array. So that's 0 and 1. So this is one way of slicing an array in Q#. You say the start element, ... just means we're going up in steps of 1. It's the default. You can specify a different step if you decide. And then we're stopping at 1. So all this is going to do is give us 0 and 1, the first and second elements. And then we specify the target, which is going to be, register 2, always with a semicolon. So this is going to take us from our 1, 1, 1 state to our minus 1, 1 state. Right, we've applied the phase shift. But now we've applied a phase shift to a 1, 1, 1 state, whereas the marked element that we want is obviously 0, 1, 0. So we need to undo those two X operations from before. And now we go X reg 2, and then X reg 0. And that brings us from minus 1, 1, 1 to minus 0, 1, 0. And thus we have applied a phase change only to the marked element, the one that we're looking to measure out at the end of this. Fantastic. Now we're actually going to use this trick another time, a bit later on in Grover's algorithm. And in this case, we don't want to reflect about the marked state. We want to reflect about the start state, that uniform superposition, all pluses. So in this instance, we want to take plus, 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 and turn it to this. How do we do that? First things first, we need to generate the all ones state, just like we did. If you hopefully remember, Hadamard will take plus to 0. So what first thing we're going to do is we're going to use apply to each in Q sharp. We're going to say we want to apply the Hadamard to each of the qubits in our register. That's going to take us from plus, plus, plus to 0, 0, 0. Great. Then what we want to do is turn that to 1, 1, 1s. So again, we use apply to each. Hopefully you're getting a kind of inkling of what's going on here now. We use X. That will take us from 0, 0, 0 to 1, 1, 1. Great. Now again, we apply the controlled Z, and then we undo the previous two apply to eaches, which will take us back to plus, 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 but now with a minus phase. Exactly the same trick. It's called changing the basis. And it's really useful for kind of other operations and things later on. And this is what that looks like in Q sharp. So we've already seen this. One useful thing to note with Q sharp is we can use this message operator. This allows us to write things out to console so that we can, for example, in this case, understand what we're doing, where we are in the algorithm as we're printing out results. We then do this familiar application of our two X's to the first and the last elements of our database register. This brings us to our 1, 1, 1 state. We then applied our controlled Z. This is the control functor like we saw earlier. We can use this syntax now as well. So I introduced this way of referring to a slice of a database, but because taking all but one all but the last element of a qubit register is such a common thing to want to do in a quantum algorithm, Q sharp has it for you. So if you say most, that will take all of the elements of a qubit array other than the last one, and if you do tail, it just takes the last element of an array. That's kind of handy, but it's equivalent to these two representations, which I showed previously. Up to you. Now, you might be curious as to what this within apply thing is doing. So this is a within apply block. What it does is it does whatever is in the within block first, so those two X's to take us to 1, 1, 1. Then it does what's in the apply block, the controlled Z, to take us to minus 1, 1, 1. And then it undoes whatever was in the within block. It does the adjoint, which takes us back to our minus 0, 1, 0, which is exactly what we want. Fantastic. Which leaves us with this. Again, if I take a measurement now, I'm equally likely to see any of those qubit states, but we've applied a phase shift. The next thing we want to do is reflect about the start state, that plus, plus, plus. This is what we saw in when I was writing in OneNote earlier. So what we do is we take these deltas, so this is the delta between the average amplitude and the magnitude of the probability amplitudes, and we reflect. Couldn't figure out how to do a rotation animation there. But this is what we get. Now, if I take a measurement, I am much more likely to see the kind of heavily increased, I'm much more likely to see the 0, 1, 0 state because of that heavily magnified probability amplitude for the marked state 0, 1, 0. And I'm much less likely to measure any of the other states. Fantastic. So we've already walked through this in kind of writing. What does this look like in Q sharp? Again, we're making use of this handy within apply so that we can do the operation, the control Z, and then undo that preparation of the O1 state. So the first thing we do is we apply the Hadamard again to take us from O plus to O0. Then we apply X to each qubit in the register to take us from O0 to O1. Control Z, again, using this most terminology, or you can use the slices like I showed previously. And then we undo those two, the application of the X and the Hadamard, to bring us back to the uniform superposition, which we started with. Fantastic, which leaves us with this. Now, putting this all together, what we want to do is actually, instead of just doing this once, we want to do it many times, so that it's very, very unlikely that we'll ever measure anything other than the marked state. Of course, still a possibility, but very small possibility. So what we do is we repeat this. We have to repeat those 2 rotations of the order of root n times. In this case, we have n being the number of elements in our database. In this case, 8. So we're going to repeat it twice. So in this case, n iterations is 2. This is a for loop, much like you will see in any other coding language. So we say for index in 0 to the number of iterations we specified, -1, so we don't end up having one too many. We're going to do our 2 reflection steps, reflect about marked, then reflect about uniform, twice in this case. And then we're going to return the result of this for each statement. Now the for each is another kind of useful Q# feature. What it does is it applies whatever we put in the first argument to all of the qubits in a register that we pass in as an array. In this case, it's going to do m reset z. Now what that does is it takes a measurement of a qubit in superposition, or a set of qubits in this case. Oh, well, sorry, it does it one by one. And returns us a 0 or a 1 result. It then, the reset z part, sets that qubit back to our nice starting state of 0 in order to have it be ready for use by another part of the program later. This using statement is key to this. So this allocates us some qubits for use within that using block, much like you might have seen in C#. And then it requires that we return those qubits in that 0 state so that it's ready for reuse later. Now you'll notice here that the return type here isn't unit as before. It's actually got a return type of result, a result array in this case. That's just going to be the array of results that we read out from m reset z here that we're returning. So to summarize, we've prepared our states for search. By doing the Hadamard on all of the qubits in the array, in the register. We selectively apply the phase shift just to the marked element 0, 1, 0 by reflecting about the marked state via that trick of basis changing. We then invert about the average, which we do by reflecting about the start state of +++, again using that trick. Then we repeat those 2 steps a bunch of times, twice in this instance, but more if you had a bigger database. And then we take a measurement and see what we get out, which is hopefully the marked element. Let's see that in action. So here we are in Visual Studio. This is the code that we have kind of been looking at for the last while, so it should be no surprise to you at this point. This is the main point of entry to our quantum program. I've called it Grover Search. What we haven't seen so far is what does the classical driver code look like, and this is it. So it's a C# I chose to use in this case. Could have used Python, as I said. Here we declare our number of qubits and the number of Grover iterations. Of course, this can be done programmatically. I chose to hard-code it in this instance just to simplify the demo, but of course, in practice, this would be flexible. This is the key line. This is the single line of code that we would need to change in order to run, either on the simulator or on real hardware or on a resource estimator. So in this case, we've chosen to run it locally on my machine using the quantum simulator, but we could just as easily have put, say, resource estimation or estimator even to see. It doesn't actually run the program, but it tests what resources would be needed to run it. Alternatively, we could have said, say, IonQ or Honeywell hardware or QCI, and that would run it in Azure Quantum when it's released, of course. So the single line of code is the kind of key one for kind of benchmarking different types of hardware and software. The next important line is this one, which of course runs our quantum algorithm. So it says Grover Search, which is what I call that Q# operation, .run. I pass in the simulator, the number of qubits and the number of iterations, and then the .result says just wait for it to return something, which is of result type. So I do that, and then all we're doing is printing this result that we get back out. Obviously, we could do something more sophisticated, but it's just a demonstration in this case. Ignore the red squiggly line. My Visual Studio is playing up. It actually is working. So now we're going to actually run it. It's running again on the simulator. We see, we're stating what element we're searching for, 0 and 0. You see that it's done 2 instances of that Grover iteration, reflecting about marked and then reflecting about the start state. And out at the end comes 0 and 0, the state that we were looking for, that marked state. Been a success. Great. In a nutshell, was Grover's search algorithm. Thank you very much for joining me today. If you're curious to learn more about quantum computing, I do encourage you to have a look at these links. The first one will give you a bit more information about what's available, well, what will be available on Azure Quantum. It will allow you to sign up for the private preview. There is comprehensive documentation available at docs.microsoft.com/quantum. This includes a whole bunch of kind of basic tutorial information, information on all the different libraries available through Q#, and obviously all of the kind of documentation around Q# itself. If you're interested in downloading the Quantum Development Kit, that's available on the third link. That's again available on Mac, Linux, Windows, whatever it is. You can run it install free via like Binder from the GitHub page directly, actually. And then if you're looking to, kind of maybe contribute to the open source Q# libraries or the simulator or whatever it is, please go check out the GitHub link there, the first one. I would really, really recommend you checking out the second one there, the quantum katas. These are a sequence of challenge-based tutorials where it'll take you from, even the basics of kind of complex arithmetic all the way through to learning how to write quantum algorithms in a kind of step-by-step way. So it kind of gets harder as you go along. Really, really solid resource. Would definitely recommend checking it out. It's been an absolute pleasure speaking to you today. Please don't forget that we've got a live Q&A coming up now. So if you have any questions, now's the time to ask them. And with that, I will say goodbye. Thank you very much.
Hi, everybody. Thank you very much for joining us today. Really appreciate your time. Now we're into the live Q&A portion. So throughout the session, we've received lots of really great questions. I tried to answer a few in the text chat, but I'll kind of pick out a couple of the common ones, for example, and try and answer as many as we can. And one of the most common ones that I've kind of seen popping up in the chat so far has been, as someone from a software developer background or a kind of an engineering background, but not necessarily in physics, how would I get started, with this kind of quantum computing stuff? How do I learn to become a quantum software engineer? And my best suggestion for you would be if you check out the links in that resources section that you can see on the webinar platform. There'll be some really good starting places for you to start learning about this. I'd in particular like to draw attention to the quantum katas link. So these are kind of a challenge-based tutorial kind of sequence of problems, effectively. So you can kind of, it's in a big Jupyter notebook, and each little section has a couple of questions, and you can type your answers and then run the script, and it'll give you a hint if you get it wrong, for example. And that starts from just learning the very basics of complex mathematics, all the way through to implementing algorithms and kind of much more complicated things. So I definitely recommend that. I think that's been for a lot of so we hire a lot of software engineers in the quantum team, not people with physics backgrounds, and a lot of them have said that the katas have been really, really helpful. The other side of it, from a physics background, I'd recommend learning, learning some kind of software engineering principles like, learning a language such as C# or Python, something object-oriented, that will kind of get you started with the more software engineering aspects. Personally, I found a book called the Imposter's Handbook a really good start. Kind of gives you a good cover of the topics in software engineering that you might not know even exist as someone from a scientific background. So I'd recommend that from the other kind of side of the fence. I had a good question. Someone asked, so you say that these quantum computers run at almost 0 Kelvin. So we're talking in the millikelvin range. Isn't that really expensive, really hard to do? Isn't that going to be really energy intensive? And actually, that's an interesting question because, yes, to get something down to that temperature takes, first of all, a long time. Like that'll take a few days in one of these kind of quantum, as we call them, dilution refrigerator. But that kind of part takes a lot of energy. But once the system is actually sitting at that temperature, unless you have a kind of catastrophic leak somewhere in the system and you lose all of your liquid helium, it's actually relatively little energy to keep your at that super low temperature once it's already there. The other part of that question was, well, if it requires all this highly specialized hardware and it needs to be kept at these super low temperatures, will that mean that barely anyone's going to have access to things? And the answer to that question is, honestly, most likely the model for quantum computational kind of availability will be like the cloud computing model. For example, through Microsoft Azure Quantum, for example, you will have access to quantum in much the same way as you can access GPU machines, for example, to do machine learning workloads. And you can kind of think of these quantum machines as co-processors in the same way as you would use a graphics processing unit, a GPU, and a machine learning algorithm. Well, on a quantum computer, when it's going to provide you with speed up. Now, this doesn't mean that we're going to, in 20 years' time, all be running, I'll be playing PC games on a quantum machine, because just like with a GPU, it would be expensive and honestly kind of a pain to code for it when a classical machine is already available, it's cheap, it's highly optimized, and the quantum machine isn't going to give you any particular speed up. So we're kind of going to move into this future where we have these quantum and classical co-processors, and we use each of them to their strengths. We also had a few questions around the kind of cryptography angle. Something about I think there was a question about the impact on blockchain. So we have, as I mentioned in the webinar, a team that are looking exclusively at post-quantum methods. So I linked their homepage in the webinar chat, so you can hopefully see that and kind of go investigate if you're curious. There are also ways in which we can use a quantum computer to exchange information more securely. So, for example, we can exchange keys using something called quantum key distribution. And due to some kind of fundamental properties of a quantum computer, for example, we have the quantum no-cloning theorem. This means that we cannot copy a stream of quantum information. We can't. If someone was listening in to your communication channel, they wouldn't be able to copy that and then kind of read out, which means that they have to be listening to your unique channel of communication. And because the states that you're sending to transfer your key are quantum states, any observation they make will cause measurements, will cause errors in the key that you actually get out at the other end. So we can actually use these quantum phenomena to encrypt our information more securely, as well as to crack things like RSA. So there's kind of multiple ways of kind of approaching those. What else did we have? So we had a few people asking about what the kind of biggest challenges of quantum computing are. Honestly, the really big challenge right now is, as I kind of said in the webinar, it's noise. Getting a system that is sufficiently isolated from the surroundings, that don't interact very easily or are just inherently stable, will have long gate lifetimes. This is really, really hard to engineer. There are some really great leaps being made with things like superconducting qubits, ion traps, systems. As I mentioned earlier, hopefully topological qubits will also help us tackle these issues. But right now, it's really the kind of key thing that's preventing us from having these machines available at scale. Another common question I saw in the chat was around quantum machine learning. So, kind of how can we apply a quantum computer to speed up a machine learning algorithm? Now, as I again mentioned, one of the bigger problems here is that trying to input big data into a quantum machine is not particularly efficient. It takes, a lot of processing time to encode classical information into a way that a quantum computer can kind of deal with that data. So the optimal kind of use case here is we use a quantum computer for accelerating specific parts of a machine learning pipeline. For example, you kind of have a hybrid approach where kind of some computationally complex subroutines that would actually benefit from quantum speedup can be outsourced to one of these quantum processors. Should also be able to efficiently solve systems of linear equations and perform matrix inversions. So those have relatively small inputs and outputs. And we can also use actually what we Grover's algorithm. We can actually use that amplitude amplification to efficiently search a problem space, for example. These are some examples. Most recently, we have released a quantum machine learning library for Q#. I linked that in the Q&A chat, so please do have a look at that if you're curious to learn more. Just going to read through some of these new questions. Actual and practical examples of quantum computers. Okay, so the example that I give most frequently is around the simulation of kind of these, as I mentioned at the very beginning, of systems which have electrons that are highly correlated. So, for example, nitrogenase. So, nitrogenase is an enzyme. It is capable of taking nitrogen and hydrogen at room temperature and producing ammonia. Now, this is significant because we need to produce ammonia to make fertilizer, to fertilize our fields, to grow crops, to feed the human population. At the minute, the majority of this ammonia is produced through something called the Haber-Bosch process, which takes incredible amounts of energy. So you have to run nitrogen over a catalyst at 400 degrees Celsius and at 200 atmospheres of pressure. And that, as you might imagine, is not a very efficient process. In fact, it uses something like 1 or 2% of the global energy production every single year just to do this. So if we can actually use this nitrogenase enzyme to do this at room temperature and pressure, this could be huge. It could have huge impact for something like, for things like climate change, for global warming. Unfortunately, because the active site of nitrogenase includes a compound called FeMoco, which includes iron and molybdenum atoms, we're unable to actually simulate the electronic configuration there to high enough precision to actually kind of to produce at an industrial scale. So this is an example of a concrete application of a quantum computer. We have any PC simulation programs that can actually help us to test our code? Yes, the quantum development kit comes bundled with a number of different simulators. These not only aim to simulate the full quantum state of all of the qubits in your quantum algorithm, that you need to use for your particular algorithm even. But they also include resource estimators. And in fact, our quantum research team, our algorithms research team, actually use these simulators and resource estimators daily to help us optimize our algorithms so that they'll run on the smallest set of hardware available, which will mean that we'll be able to run them as soon as possible. So yes, if you're interested, you can absolutely run these. You can run them locally. It all comes for free. You can get about 30 qubits to run on a local machine if you have about 16 gigs of RAM and no web windows open using up all of the RAM on your machine. I think we're probably running out of time, so I will answer one more question, and then we can wrap. Sorry, I'm just reading through them. Right, okay, so there's a... Oh, no, it's quite specific. There's a question about internships, actually. Yes, absolutely. If you are engaged in quantum computing, in quantum, in a physics degree or in a computer science degree, maths degree, these kinds of backgrounds, we actually have a summer internship program that runs every year. We take candidates from across these disciplines. We usually have both an engineering and a research flavor to these internships. And during them, you'd actually be working directly alongside our quantum research team or the quantum solutions team or other kind of members of the quantum product group to build solutions, to build new algorithms, and to kind of, further the field as if you were just, one of the team. So I'd absolutely encourage you to have a look and to join us for a summer. We'd love to have you. And please feel free to have a look. It'll be on the Microsoft careers site or the Microsoft Research careers site. You should be able to find those through a web search. All right. Well, I think that's all we have time for today. Thank you so much for attending. We really appreciate your participation and your interest in the subject. There have been some great questions. If you are interested in learning more, please do check out the resources that are linked. This will be made available on demand. You should get an email with the link once that's ready. And I look forward to seeing what you can contribute to the quantum computing space in future. Thank you very much.